A heartily welcome viewer and welcome to my Tech Talk video. Before starting this Tech Talk, let me introduce myself. My name is Bhuvneshwar Sankranti and I am currently pursuing my undergraduate BTech degree from Institute of Aeronautical Engineering, which is basically located in Dundigal, Hyderabad. And I basically belongs to Computer Science CSC A section, and my roll number is 21951a0527, which you can see on my screen or my PPT. And without further delay, let's move into our today Tech Talk video. Let's go. Tech Talk topic. Today our Tech Talk topic is from the subject Basic Electrical Engineering, which commonly referred as BW, and my Tech Talk topic is Transformation of Electromagnetics, an overview of an theory and the application. In this total Tech Talk video, I am going to cover about this topic, transformation of electromagnetic, and overview of theory and applications. Topic learning outcomes. Name of the topic: transformation electromagnetics, an overview and theory and the applications. Topic learning outcomes. We will going to learn theory and applications of the topic. In the whole TikTok video, I am going to explain some theory and what is clocking and polarizing splitters and all the theory, how to convert, how to transform the electromagnetics and all the stuff. And I am going to give the conclusion and how different methods are used to transformation the electromagnetics and some of the applications. By end of this TikTok video, you will going to learn this all. Okay, here is the introduction for today our TikTok topic. In this slide I am going to discuss the introduction, a brief introduction about today's topic. The recently introduced transformation electromagnetic techniques provide a new methodology for designing devices that possess novel wave material interaction properties. They are based on the form invariance of Maxwell equations under coordinate transformations. The whole transformation of electromagnetic techniques is based on the Maxwell equations, which is under the coordinate transformation, under the coordinate transformation means there will be in further slides I will going to discuss about this Maxwell equation. There you can figure it out what's meant by Maxwell equation there. And this method provides an extremely versatile set of design tools that employ spatial coordinate transformations where the compression and dilation of space is different coordinate directions are interpreted as appropriate scalings of the material parameters. The most famous transformation optic device is clock invisibility. In this whole Tech Talk video, I am going to mostly focusing on this clock of invisibility, because the most famous of transformation this is the most famous transformation optical device. So we will focus mostly on this one. However, a wide variety of other devices are possible, such as field concentrators, polarization rotators, beam splitters, beam collimators, and flat lenses. In this paper, an overview of transformation electromagnetic device design techniques is presented. That this whole Tech Talk video begins by introducing the underlying design principle being transformation electromagnetics. Several novel transformations based devices are then summarized, starting with electromagnetic clocks that have special shell or cylindrical angular shapes. More general clocking designs of non-circular angular geometrics are treated, and the application of clocking of RF microwave antenna shielding is also discussed. In this whole Tech Talk video, I am going to discuss these all things, which are electromagnetic clocks which have special shell or cylindrical angular shapes, more general clocking designs of non-circular angular geometric and treated, and the application of clocking of RF microwave antenna shielding also discussed. Here, following in this slide, following these designs that employ transformations that have discontinuous on the domain boundary are presented. Unlike those used for clocks, this type of transformation is capable of modifying the fields outside of the device. Example of this type of transformation: electromagnetic devices are presented, which include flat near field and far field focusing lenses, wave collimators for embedded sources, examples antennas, polarization splitters and rotators, and right angle beam benders. Okay, we will move into the further slide. Okay, in this whole Techtalk video, we are going to learn this. What we are going to learn. What we are going to learn means in first coordinate transformations, form invariance of Maxwell equations, transformation electromagnetics, clocking, carpet clocking, other applications, and concluding remarks. In this whole Techtalk video, we are going to discuss coordinate transformation, form invariance of Maxwell equation, transformation electromagnetics, clocking, carpet clocking, other applications, and at the final I am going to give the conclusion. Okay, let's move. Maxwell equations are form invariant. What is the Maxwell equation? I will discuss. In any coordinate system, Maxwell equation can be written as Maxwell equation can be written as delta cross H is equal to JW in psi of E bar. See here, these equations are for Cartesian coordinate, these equations are for cylindrical coordinate, these equations are for spherical coordinate, these equations are for Martin coordinates. But what's the difference here? We can't find any difference here. Maxwell equation is invariant for any coordinate form. The Maxwell equation can be saved. By seeing this on my PPT, you can demonstrate that Maxwell equation for any coordinates. If you take for Cartesian coordinate or cylindrical coordinates or spherical coordinates or Martian coordinates, for any coordinates which exist, the Maxwell equations are same. So by that we can say that Maxwell equations are invariant. We can transform Maxwell equation to different coordinate system, but they still have the same form. See, by this line, once see this line, we can transform Maxwell equation to different coordinate system, but they still have the same form. See, in every system Maxwell equations have the same form. Concept of transformation of electromagnetic. In this slide I am going to discuss about the concept of transformation of electromagnetic. Transformation electromagnetics is an analytical technique to calculate the permittivity and permeability function that was bend fields in the prescribed manner. The basic idea of transformation electromagnetic is to find the analytical and technical of calculate the permittivity and permeability of a function that will bend fields in a prescribed manner. Okay, see here, see the first graph. This graph defines a uniform grid with uniform rays. See here, there is no bending or something. This ray defines a uniform grid with uniform rays. While coming to the second graph, this graph performs a coordinate transformation such that the rays follow some desired path. In this graph, the rays are following a desired path. Performs a coordinate transformation such that the rays follow desired path. While coming to the third graph, in this third graph, it describes that incorporate the coordinate transformation into the material tensors. These three graphs will demonstrate you concept of transformation of electromagnetics, basically which we calculate the permittivity and permeability functions. Here in this slide we are going to discuss what is clocking. I am going to give the basic idea of what is meaning of what is meant by clocking. Here you observe these two graphs. First I will discuss these points. A true clock must have the following properties. To be a clock or to be an ideal clock, these two properties must satisfy to be a clock. Cannot reflect or scatter waves. To be a true clock, it should not reflect or scatter the waves. When we send the waves through the clock, it should not reflect or scattering them. What is meaning of reflecting? We don't know. Just reflecting as a reflecting of light, or scattering. Scattering means when it absorbs light, it don't want to split all the rays into 360 degrees in the same amount. It should not do that, this reflection and scattering. And the second property, must perfectly reconstruct the wave front on the other side of the object. So it must reconstruct the wavefront on other side of the object also. As if you send the one wavefront inside from the beginning, it should reflect the same on other wavefront on the other side of the object also. See here the graph. Here is the object. Here is this place. So it is a clock because here the in front wavefront and the back side also the wavefront are the same. See observe the graph here. X, we take x in meters and y2 in meters. X in meters and y2 in meters. This is the example of clock. See, this is the electric field this is the electric field. If by observing this graph you can demonstrate what is clocking. here in this slide we are going to discuss famous cylindrical clock. This is see, observe the difference between these graphs and this graphs and this graphs and these graphs. See what's where if I can here we can find the cylindrical shapes here, but here we found just wavefronts like circles here. Here we found this wavefronts in the form of cylindrical. In the see, let's assume as this figure 3. Figure 3, a two-dimensional circular angular clock. A conducting cylindrical subjects to TM model plane wave illuminations. In the figure B, the same conducting cylindrical clocked with the clock. Same, we took the same plots x and y, same plots, and this is the magnetic field, and this to be the magnetic field. The whole only difference is the shape here is circles like, and the shear shape is the like in cylindrical. Problems with, in this slide we are going to discuss with problems with clocking by transformation electromagnetic. The resulting materials are anisotropic. The result after getting the resulting material will be anisotropic, requires dielectric and magnetic properties. It should require the dielectric and the magnetic properties, requires extreme and singular values. It's also require the singular and the extreme values. Particular problem at optical frequency. At this, they are also having the particular problems at the optical frequency. Three cases of clocking. Here in this slide I am going to discuss about the three cases for clocking. Squish an object at a point. This as a point we are going to squish an object at a point. Squish an object to a line. We are discussing about the line. Squeezing an object to the sheet or a plane, we can call it as a plane. To squeezing an object to the sheet. Here we took a point, as in the space we took a point, and here it is 2D, we take a line. This to be a 2, we can consider as a 2D, but it has the length, breadth and height. It has only length, it has length and height also, height also. We can assume thickness as 0. Object, here see, for this 2, object becomes, for point and the line, object becomes infinitely conducting. This is not problem because the objects have 0 size. As the objects has 0 size, it will not have a problem. Does not has any problem. This can be rendered invisible, but require extreme and singular values as well as being anisotropic. For now, for this sheet, a sheet is highly visible. It can only be made invisible if it sits on another conducting sheet, so they can't be recognized, or we can't find any difference there. While more limited, invisibility can be realized without extreme values and with an isotropic material. These are the three cases of the clocking. Here in this slide we can find this object, line and the sheet. These are three examples of three cases of clocking. We will move into the further slide. Electromagnetic clocking of antennas. What are electromagnetic clocking of antennas? An antenna can be clocked to either render it invisible, to be bad guy, or to reduce the effects of scattering and coupling to nearby objects. An antenna can be clocked to either render it visible to a bad guy or to reduce the effect of scattering and coupling to nearby objects. This implies a dual band mode of operation because the clock must be transparent to the radiation frequency of antenna. Metamaterials used to realize clocks are inherently narrowband, which is an advantage for the application. Here, the metamaterials used to release clocks are inherently narrowband, which are advantage for this application. Here in the slide you can see the electromagnetic clocking of antennas. First, antenna A, this is antenna A1 transmits a frequency of, let's assume antenna A1 transmits a frequency of F1, antenna A2 transmits at frequency F2. This antenna A1 will transmit at a frequency F1, and this antenna transmits frequency F2. Now clock A1 must be transparent to F1. Clock
A2 must be transparent to F2. Electromagnetic clocking of antennas. These conditions must satisfy, and this both graphs or this both images will demonstrate you these examples. Here in the A1 transmits through unclocked A2. Here A1 transmits to unclocked to A2. Here A1 transmits to clocked A2. Here A1 is transmits. Now here this A2 is clocked, and here this A2 is not clocked. Here A1 is transferring through clocked A1 A2, and here A1 is transmitting through unclocked A2. This is the difference, whole difference between this one and this one. Now another we are entering to the another new topic, another one, polarization splitters, which can alternately use for the clocks. Polarization splitters are also one of the major topic. The device which is polarization splitters is made uniform in z direction. Maxwell equations split into two independent modes. Each mode can be independently controlled. We can control each mode independently. And here see graph A E mode, and this is H mode. Here we can see the difference. Here it will be like this, and here in H mode the graph will be like this, and the coordinates will be the same. This is E mode, and this is we call as Z mode. Polarization rotators. Now we will see about, before we seeing about the polarization splitters. Now we are going to see about the polarization rotators. Now see here how the lines are going to rotate here. As we discussed here, device is made uniform in the z direction, in the along the z axis. In it's now it's rotating along the z direction. See, as before it is like this, and after completion of polarizing rotators, it's going to the clock here, clock or the what we call this an object will be rotating like in the z direction in the clockwise or anti-clockwise. Here we can see the electric field intensity. Wave collimator. In this slide I am going to explain the wave collimator. These are the wave collimators. See in figure 16, samples of the eye polarized total electric field distribution due to the electric lines solver located at the coordinate origin A. This is for the A with the line source regarding in the free space, and this B with the line source enabled to the wave collimator. And the coordinates will be the same, and this reflects the electric field intensity. Beam benders. Now we will discuss about the beam benders. These are the graphs for first, while before going to pass, this will be the graph. After passing through the beam benders, now the graph will be located like an, as the name suggests that it will bend like a beam. Name suggests that the graph will be bent like this here. Here see practical application here. Okay, we come to the conclusion of the Techtalk video. What we learned till now: transformation electromagnetic is a coordinate transformation technique where the transformation is evolved into permeability and permeability function. As we discussed in the first two slides, first three slides, transformation electromagnetic is a coordinate transformation technique where the transformation is absorbed into permeability and permeability functions. The method produced the permittivity and permeability as a function of position. These methods produce the permeability and permeability as a function of methods. The method does not say anything about how the materials will be released. These methods will not say anything about how the materials will be released. The resulting material function will anisotropic and requires dielectric and magnetic metamaterials with often extreme values. This leads to the structures requiring metals. TEM. TEM is perhaps more commonly called transformation optics TO because that is where it first appeared. Basically, T is perhaps most commonly called as transformation optics TO because it is where it is first appeared.
And this is the last slide of my video, or we can call as the Tech Talk video. Thank you, viewers. And this is the my Tech Talk video. And once again, I have to thank you for spending your most valuable time here in my Tech Talk video. Thank you.